last time we start looking at what's called the Riemann integrals. So we have, for the Riemann integral, we have a function, f, that is defined on some interval from a to b into R. And this function is bounded. And then we have a P here is a partition of this interval. And so this means that we have a number of dividing points where A is the first, and then we have x1, x0, that is A, x1, x2, and so on, up to, say, xn, and that is the final point, endpoint of the interval. So this here is a partition. You know, these are the dividing points. Then we look at the length of each of these subintervals. So we have the subinterval from xi minus 1 to xi. And the length of one of these subintervals we denote by delta xi. And so this is xi minus 1. And then we look at, right, so here if you have the function here, this is the function f. And here we have the interval from a to b. And so this here is the first dividing point. This is the last dividing point. And then we have these other dividing points in between. And this is maybe x2, like that. Then we look at the function on one of these subintervals. So we look at the function, and we restrict it to one of these subintervals. Right. And then remember the function is bounded. And so we're looking at it on one of these. And we defined capital Mi to be the sup of f over this subinterval. And we defined, likewise, we defined little mi to be the inf. Right, and this makes sense, the finite number, because the function is bounded. And then we look at the upper and the lower sum. So the upper sum. So the upper sum is that we have this given partition, and we look at the sum here of the mi times delta xi. And we're summing, this is from 1 to n. So this is the upper sum of the function for this partition. Right? And likewise, we look at the lower sum. This is where we sum the infimum, and we weight them by the length of the intervals. So we look at mi, and then delta xi, and I equal to 1 to n, and this is the lower sum for this partition. And then just using that, so of course for these mi, right, this here, it's the infant sum on the same interval. So little mi is less or equal to capital Mi. Right? But this also means, right, that these weights are the same. If this here is less than that, it means that the lower sum is less or equal to the upper sum. Now, the second thing we looked at is, so again, we have this partition P, and we looked at P1 as a subpartition. Subpartition or refinement. This is if P1 has the same dividing point as P, and then presumably some. Then some more. Right. I mean, you could have that. You could have that the two partition was exactly the same, and you would still say that one is a trivial subpartition of the other. But in general, right, a subpartition would have more dividing points, right? And so then the thing is that if you're looking at, so let's say that so that P here again has the partitions. This is the partition that comes from P. And let's say that P1 here, let me illustrate it as if P1 have one additional. So here you have x0, which is A. Here you have xn, which is B. And then you have two others, say this is x1 maybe, and this here is xk. And then you have a bunch of other. This is the partition P. And then P1, let's say, have one more dividing point. It could have many more dividing points. But if you're looking at, so you have here xi minus 1, and then you have xi, and then maybe the P1, this partition, have an additional dividing point. It's called that y. Right? Well, then the contribution that you get from to the lower and upper sum. So the contribution that you get from this or that for P, you can think about that as Mi. This is the contribution from the lower sum, and here you have the contribution from the upper sum. But now, now you see that that for the subpartition, then you have that, so the intervals for the subpartition, this here is the interval for the original partition P, but for the subpartition, this is now divided into two intervals, this here and that here, right? And so you have that, so this thing here, this is, in this case, is split into two, and one of them is y minus xi minus 1, and the other is xi minus 1. Right. Now, if you're looking at the, say, the lower sum for this subpartition, right? So this thing here, so the contribution that you get from this here, well, you have two intervals, and so you're getting a contribution which is the inf on this thing here, on this little interval here of f times y minus xi minus 1, and then you get a second contribution which is inf on this interval here from y to xi of f, and then it's xi minus 1. Right? So this is a contribution that you get from this interval here. But this thing here is smaller or equal to the, it's actually, sorry, this here is larger or equal to the inf, where you take the inf over the larger interval that goes from this point to that point, right? So you have that this is larger than y minus xi minus 1. This thing here is also larger than this little mi, and then it's xi minus y. And now you can just factor out, so you're getting mi, and then when you add these two together, right, then you see that this gives you exactly xi minus 1. So this is little mi times delta xi, right? So this means that if you, so you see that the contribution that you get on this little interval for this is larger than the same contribution that you get from this, larger or equal to, right? And so when you're summing over all intervals, then you get that if P1 is a refinement or subpartition, then this lower here, the lower sum, go up. So this lower sum go up. And if you do it now, if you do the same stuff for the upper sum, then this here would, instead of being inf, it would have to be the sup. This here would have to be the sup. But the sup on the smaller interval is now, then this inequality will reverse. It's less or equal to, and then it will come to sup on the larger interval. This here remains the same. This here again becomes a larger one. So this here becomes less than this. This here becomes less than this. And so what you see is that the sup here go down, right? So the lower sum go up, and and if you're looking at the upper sum, this here decrease. So you have that, right? And so putting this together, you have that that the lower sum for the partition P is less than the lower sum for this subpartition, which is less than the upper sum for the subpartition, which is less than the original upper sum. Okay, so you have that. And so this is like a key fact. It's sort of an obvious fact, but it's a key fact. Okay. So now, so that was the upper and lower sum. So now we define the upper and lower integrals. So we define the upper and lower Riemann integrals. We define them as follows: that the upper one we denote like this, and this here is now the inf of all partitions of the upper sum. And likewise, we define the lower Riemann integral of this function, this bounded function, to be the sup of the lower sums, like that. So sup of all partitions. Okay, so that is the upper and lower sums, Riemann's integrals. And so now we say that the function, this bounded function, f, is Riemann integrable. So F here, so F is said to be a Riemann integral and we write that F here is like this, so it means that it's Riemann integral. If the following is the case, so if this lower integral here is equal to the upper integral, and if this is the case, then we just write, and then the Riemann integral of F is then denoted by just like that. Okay. And so this is Riemann's way of defining integrals. There are other ways, but this is, I think this was the first way where you have a definition that really made sense. Okay, so now the first thing I want to observe is that for a general function, you always have, so in general, so we always have, whether the function is Riemann integrable or not, we always have that the lower integral here, the lower Riemann integral, is less or equal to the upper. And so why is that the case? Right? So this is because this is because if you take a partition, so fix a partition, then you have that the lower sum here is of course less or equal to this thing here, right? Because this here was the soup of all partitions. So you have that, right? But in fact, what you also have but more importantly, you have that this L of F here, I claim that this is less or equal to the upper sum for any other partition, for any partition. So I claim that you always have this here. If you take two partitions, P and P star, then the lower sum for one is less or equal to the upper sum for the other. Why is that the case? This just uses that inequality over there. It uses that together with this inequality. So let's see. So if P here is a partition, and P star is a partition, then you could take a partition, so let P bar be the partition, that has all the dividing points of P and all the dividing points of P star. Right, so the dividing point of P bar is a union of the dividing points of the two partitions, right? But this means that P bar here, so P bar here is a refinement. It's a refinement of subpartition of both P and P star, right? Because it has all of the dividing points of either, right? But this means that, remember that the lower sum, so if you're looking at this, the lower sum, if you take a subpartition, that goes up, right? So if you take a subpartition, the lower sum will go up. But the lower sum is always less or equal to the upper sum for a given partition, right? But this here is now a refinement of P star. So the upper sum go down. So this here is less or equal to U F of P star. Right, and so there you have it, that this thing here, the lower sum for one partition is always smaller than the upper sum for the other, right? And so this means that if you now take a partition, so now it means that for a fixed partition, P, so we have that this thing here is less or equal to this. Think about P as being fixed, but this is now for all partitions P star. So this is for all P star. But if it holds for all, this here is is less or equal to. If it holds for all, then it also, this inequality, this is a fixed number. This means that this here is a lower bound for this family. So this means that L F of P is less or equal to the nth of those guys. Right? It's less or equal to the nth. But that here is just this here is by definition the upper Riemann sum, upper Riemann integral, right? But this is for each, so now you forget about the P star. You have that this thing here is less than that number. So this means that this number here is an upper bound for this whole family, right? So this means that also the sup, the smallest upper bound, must be less than that, right? So this means that the sup of L F of P must be less or equal to this thing here. But the sup is by definition the lower integral. Right, so you always have, and this is this claim over here. Right? Okay, so that's the first. Let's look at let's look at a function that is. I added it just a little bit. If you find it interesting, I find it interesting, but maybe you don't. But a little bit about Riemann, that he died rather young of tuberculosis, but he had an incredible impact. He had incredible, I mean, this is one of his contributions. his first contribution, he was a student of another really famous mathematician, perhaps the most famous of all time, Gauss. And so at those times when you wrote your thesis, then you had like 6 months to write your thesis,